first talk will be by on cryptographic rest, Quantummess, and Certifiable Randommess, a single quantum device.
Thanks, Nikhil. Good morning, everyone. Thanks for coming. So this is joint work with Zvika Brakersky and Urmila Mahadev, who are, if not in the audience, at least in the conference, and then also Paul Cristiano and Umesh Vazirani. So I think probably most of you were here in the talk by Urmila Mahadev yesterday, and you'll see a lot of the ingredients that came into her talk show up again here. But I'm not going to assume that you were around, so this will just be a refresher. So just to put it in one sentence, this is work that I think is interesting because within quantum... Is the mic okay, by the way? Yeah, so within quantum information, it sort of builds a connection between that allows us to import a lot of techniques that have been used in the setting that's known as Bell inequalities or multi-prover interactive proofs with entangled provers, and bring these techniques to the regime where you interact with a single device. And so at the conceptual level, for the cryptographers and complexity theorists, this is kind of analogous to the connection that was initiated by Kalai, Raz, and Rothblum that allows to transfer results about the complexity of multi-prover interactive proof systems that are non-signaling and transfer those into efficient delegation protocols with a single prover. But admittedly, the connection is much less developed in the quantum case. So I'll come back to that comment right at the end of the talk, but let me first give you a little bit of context and then I'll present the result. So I think a lot of us are aware that we're sort of undergoing an interesting phase transition in quantum computing right now. So the field of quantum computation started with a major bang in the 90s, and this was the discovery of a quantum algorithm for factoring in polynomial time, and also the discovery that there existed exponential separations in the oracle model between what quantum algorithms could do and classical algorithms could do. And this, at least at the philosophical level, forced us to reevaluate what we think of as problems that should be efficiently computable or not. But this was all very hypothetical because the machines didn't exist, right? And so since then, a lot of time has passed, and we still don't have these machines, but we're starting to get smaller kind of machines. And this is a new phase, I think, in quantum computing that my colleague from Caltech, John Preskill, has called the NISQ era. So NISQ stands for Noisy Intermediate Scale Quantum Devices. So it's the era where we don't have large fault-tolerant quantum computers, and we don't see them on the horizon yet. But we have something else that's starting to get interesting. So it's this kind of chip that's maybe 50 qubits, 60 qubits, 70 qubits. That's not a fault-tolerant quantum computer, but that can implement some computations that, at least in principle, cannot be directly simulated. And so it opens the question of whether we're finally about to see the realization of this promise from 20 years ago that quantum computing violates what's known as the efficient version of the Church-Turing thesis. And so the question then is, given that we have these devices, what kind of tests can we perform on them that allow us to distinguish them from classical simulators, imposters, that would try to fool us in believing that they're performing a quantum computation. So there's a lot of work in this direction that I'm not going to be able to survey. It's not the purpose of the talk. So this started by the work of Aronson and Arkhipov on boson sampling. There's work in a model called instantaneous quantum computation. There's work by people at Google. And so just to summarize in a sentence what these proposals do, they suggest that a test that we could perform on these small, like 70 qubit devices, is just require the device to implement a random quantum circuit and then measure all the qubits at the end of the computation. By doing so, they would sample from an n-bit distribution that under some complexity theoretic assumptions, it is hard to sample from using classical devices. So that's just the gist of it, right? Implement a quantum circuit, measure at the end, and verify that you're sampling from a certain distribution. I just want to point out a few sort of features or limitations of these proposals. And the main one is that they're really targeted at a very narrow regime in terms of the kind of devices that they can test. And when I write here 50 to 60, I really mean 50 to 60, or maybe I should broaden it a little bit, like 50 to 80 or something. So the reason you need at least 50 qubits is because if you have less than 50 qubits, then you can just simulate directly the computer, so that's not interesting. And the reason you can tolerate at most 80 qubits is that the verification of these tasks is very hard, right? So once you have the quantum machine and it samples from the distribution, in order to check that the machine is sampling from the right distribution, you need to implement a test, and that test runs in exponential time. So if you have a machine that implements the computation over 100 qubits, then you can't test whether it does so or not. And so that's a big limitation of them. Another limitation of these proposals is, I told you, I mean, they implement a random circuit, right? And so the day you've implemented a random circuit, then, what have you achieved? You've implemented a random circuit, right? And then so what? Well, okay, you have your test. But the problem is that it seems very hard, just by the nature of these experiments, to build anything on top of it, right? So can I use them in order to do something interesting? And that's not quite known. And so we're sort of an interesting picture there, where for the time when we have these 50, 60 qubit devices, then we have these tests that we can implement, and they're sort of kind of interesting. We're demonstrating something about these devices. But then there's a whole regime to the right of 50, and then by the time you arrive at 2,000 fault-tolerant qubits, and so that's, you have to multiply that by a factor 1,000 due to error correction, so there's a couple million qubits, then you can factor. Then you can implement like roughly any quantum algorithm, and so fine, right? By the time we get there, we're not worrying about anything else. But we're not going to get there tomorrow, and so there's this big regime in between where it's not clear what's going to happen there, right? So 50 qubits we'll be able to test them, and then 100 qubits, 200 qubits, 1,000 qubits, then what, right? We won't be able to implement these proposals because we won't be able to run verification anymore, and we won't be able to factor either. And so is there going to be like a period of 10 years during which we don't quite know, right? We don't know if the computer broke down because of noise at 100 qubits or decoherence or something like that. So that's sort of where this work falls, and I'm not going to answer this question. I think we're going to make an interesting step in that direction. So let me talk a little bit about our results now. So let me make the model a little bit more precise. So we're considering a scenario like this where there's a single quantum device. So this is a quantum computer to which you have access. But you have access to it through classical means. So you just have your laptop and you can send instructions to the quantum device that I really think of as a black box, right? So the instructions will say, well, please measure this, please do that. But in practice, I don't really know what's going on inside there. The only thing I get back is classical information that the device decides to report to me. And so if you think about that setting, you realize that the main difficulty comes from the fact that there's a large asymmetry, of course, right? So the classical verifier just has a classical laptop, so it's a classical polynomial time machine. And then this quantum device, I don't know what it is, but it could be a full-blown, fault-tolerant quantum computer, so it has the power of PQP. And so in order to give the verifier the means to test the device, I need to do something in order to restore a little bit of symmetry in the problem. And so the way we're going to do this is by introducing a cryptographic assumption. So the main idea is going to assume that this quantum device is computationally bounded. So just BQP, right? And then the verifier will set up a cryptographic scheme that involves a trapdoor. So this will be a classical cryptographic scheme. And the trapdoor will give leverage over the quantum device, assuming that this cryptographic scheme is post-quantum secure. And the goals for this protocol here are going to be threefold. First of all, in order to distinguish ourselves from the proposals that I mentioned earlier, we'd like this proposal to be, the protocol to have efficient verification, right? So the verifier should be efficient. And then I'd like to have something a little bit more than just a test that my device is quantum. I'd like to arrive at maybe a characterization of this device, right? Be able to say, well, it must have been measuring a qubit in this way or that way. And also, ideally, the device would be implementing something useful. For this particular talk, we'll be able to certify that it generates information theoretically secure random bits. So that's the setup. And now let me give you the protocol at a high level. It's a very simple protocol, and then I'll go a little bit more in depth, instantiate that protocol. It's going to involve only 4 rounds. And here's how it works. The verifier starts off by initializing the cryptographic primitive that I'll tell you about in the next slide. And so it sends the name of this primitive or the public parameters to the device. Then the device sees these parameters and is supposed to respond with a string y that I call commitment, where it's just some bit string y. So that's the first phase. And then in the second phase, the verifier is going to choose a challenge. There's just two challenges. They're called 0 or 1. And then the device has to provide a response. This response is, again, a classical bit string. And here's how we're going to, here's the interesting thing that we're going to do with this protocol, is that we'll set up the crypto. I'll show you on the next slide. so that it is the case that it is impossible for any device, any bounded device, classical or quantum, to simultaneously provide an answer to both challenges 0 and 1. Okay? That's something that you'd never think of if you were implementing a classical protocol, right? So why? Because if my device is classical and it cannot simultaneously answer the 0 challenge and the 1 challenge, then it just cannot succeed in that protocol, right? Because if I could succeed in that protocol, I could answer if the challenge is 0, and I could also answer if the challenge is 1, which means that I could answer both challenges, right? Because a classical device, I could run it on the 0 challenge, rewind it, run it on the 1 challenge, and get both answers. A quantum device, this is not the case. And so I have a protocol there where, at least in principle, it would be possible for the quantum device to succeed it. And just a comment, so what we're really trying to force this device to do here is perform what's known as a collapsing measurement, right? So we want it to be the case that the device cannot be rewinded. This is the opposite of what's typically done for those of you who know, for example, in the analysis of zero-knowledge protocols. Even if you analyze a zero-knowledge protocol against quantum adversaries, you design your protocol so that it is possible to rewind the quantum adversary, which is how you prove security. Here, I want to design my protocol the other way around. So let me show you how we're going to do it. So the primitive that we need already showed up in Urmila's talk yesterday. So it's called a trapdoor claw-free function. So here's my definition of it. It's just a function that maps n plus 1 bits to n bits. So it's a 2-to-1 function, right? So every image has exactly 2 pre-images. The security property is that it should be hard to find what are known as claws. So it's just a triple of 2 images that map to the same image. And we'll also assume that this function has a trapdoor. So if you're given a trapdoor, given any image y, you can recover both pre-images. So this is a standard primitive in cryptography. Let's just assume that it exists. And let's look into something interesting that you can do with that primitive using a quantum computer. And the interesting thing is just the really most straightforward thing. What you do is that you prepare a superposition over all possible inputs in the domain of the function, then evaluate the function in a separate register, measure the image, and that will have the result of collapsing the pre-image register to a superposition of the 2 pre-images that are consistent with the image that you measured, right? So just prepare a uniform superposition, evaluate the function, measure, the pre-image register collapses, and you have this superposition. Okay, now there's 2 things that you can do. The first thing is that you could just measure this register, and then you'd obtain a pre-image. So at that point, you haven't done anything interesting because a classical algorithm could do the same thing just by going at it in reverse, right? You choose the image first, x0, x1, evaluate the function, get y, and there you are. You have 1 pre-image, 1 image. Because there's a different thing that quantum computers can do, and there's the main difference between quantum computers and classical computers, is that they measure in 2 different bases, right? So this was measuring in a computational basis. I can also measure in the Hadamard basis, which is the Fourier rotated basis, and I'm skipping the calculation here. It's a standard calculation in quantum computation. You do it if you analyze Simon's algorithm, for example. And if you measure this superposition in the Hadamard basis, what comes out of it is another bit string, d, that has the property that the inner product with d and the parity of these 2 pre-images is 0. And so now what we do, and I'm not going to have time to explain during the talk, is that we give a construction of a specific trapdoor claw-free function that's based on the learning of errors problem that has a slightly stronger security property than the hard-to-find clause property that I wrote over there. So the stronger property is that we can show that it's hard to achieve the following. It's hard for any classical or quantum polynomial time, assuming LWE is quantum secure, to come up with both a pre-image, x0 or x1, and an equation, d, that has parity with the 2 pre-images. Right? So intuitively, this is a strengthening of the hard-to-find clause because this second property there, the equation, is an equation that involves both pre-images. In fact, it's a little bit tricky to come up with that, showing this, in particular because the device has the choice of the equation d that it reports, right? So if I knew this was a uniformly random equation, then I could do decoding and conclude that the device can compute x0 plus x1, but d doesn't need to be uniformly random. That makes it a little bit more tricky. Okay, but I won't say anything more about how this is constructed. I want to go back to the protocol and tell you how the protocol is instantiated with this primitive here. Okay? And note that maybe I just want to clarify that there's no contradiction on this slide, right? Because the quantum device can achieve either a pre-image or an equation But before it can get the one or the other, it has to decide what basis it's using to make the measurement in, right? And it can only make one measurement, so only get one of the two. What's hard is to come up with the two of them simultaneously. Okay, so let's go back to the protocol. Same protocol as before, except that now in the second round, on the 0 challenge, I'm asking the device to measure in the computational basis, so it should report a pre-image, x0 or x1. And on the 1 challenge, it has to report that equation. And I'm sorry, what I showed you on the previous slide is that it's straightforward for a quantum device to implement this protocol simply by doing exactly what we described, right? So evaluate the function in superposition, measure the image, and then depending on the challenge, measure the pre-image register in the computational basis or in the Hadamard basis. I also sort of very briefly argued that it's going to be hard for a classical device to succeed in the protocol, because if a classical device succeeded in this protocol with probability significantly larger than a half, then I could rewind it. And I would be able to use the classical device in order to simultaneously get answers to both challenges. This would violate the hardcore bit property of the specific instantiation of the trapdoor clock-free function that we give using learning with errors. Right? So I have a protocol. The quantum device can succeed. The classical device cannot succeed. I want to go a little bit further in the analysis. So let me tell you in just a couple of words how we analyze this protocol. So the idea, because it's a little bit complicated, right? There's a lot of information flying around. And so we want to focus on the single bit of information that we get from this device. So in the case the challenge is 0, the single bit that I'll focus on is whether the pre-image was a 0 type of pre-image or a 1 type pre-image. So there's a standard way to classify these pre-images. And in the case the device reports an equation, I'm just going to focus on a single bit that says whether the equation was correct or not. Right? So let's have just two binary measurements that correspond to these two bits. So for the challenge 0, a binary measurement that says if the outcome is the 0 kind of outcome or the 1 kind of, 0 kind of pre-image or 1 kind of pre-image. And if the challenge is 1, again, a binary measurement that is whether the equation was correct or whether the equation was wrong. And now let's go again over the reasoning that we made a little bit earlier. So this hardcode bit property, what it says is that these two measurements must be incompatible. You can't make the both measurements simultaneously, because if you were able to make both measurements simultaneously, you'd be able to get both a pre-image and an equation, and that's just impossible. It would violate the security of our crypto system. Okay, so these measurements are incompatible, and what else do I know about them? I know if I run the protocol and I test the device that it succeeds in the protocol, so most of the time it returns a valid equation, which means that whatever state it measures must be an eigenstate of the M0, M1 measurement associated with the 0 eigenvalue. But then because these measurements are incompatible, it means that when I make the other measurement, the one associated with the challenge 0, then I'm measuring a state that's unbiased with respect to that measurement, and in particular, the measurement must return randomness, right? And so this is how we get randomness out of the protocol. This argument shows that it couldn't be the case that this device always returns to me like a 0 kind of pre-image or a 1 kind of pre-image. So actually not in slightly more detail, but maybe still I want to argue how you quantitatively get randomness out of the protocol, because there's a lot of randomness that's required on the verifier side, right? So to initiate the trapdoor clock-free function, select the public parameters, and also to flip these challenges. But there we use like standard de-randomization tricks, so the function can be chosen pseudo-randomly. These challenges can be biased strongly towards the 0 challenge, which is the one that gives me randomness, in a way that you can execute n rounds of this protocol using only log squared, roughly random bits. But at each round of the protocol, then we get a constant fraction of a bit, right, from this 0 or 1 outcome that's reported on the 0 challenge. And so we get a protocol that has n rounds, can be executed using only log squared n bits of randomness on the verifier's side, but results in the generation of roughly n bits of randomness at the end. And what I want to emphasize is that the security of this protocol requires to assume that the device is computationally bounded while the protocol is being executed, so that it can't break learning with errors assumption for the duration of the protocol. But once the protocol has ended and the verifier has written on a sheet of paper all these bits that were reported by the device on the 0 challenges, at the end of the protocol, these bits are indistinguishable from random, or at least they have high min entropy, then you apply an extractor. So they're information theoretically random. If later someone comes along and says, oh, now I can break LWE, they won't anymore, it won't help them distinguish these bits from random. So they're not pseudo-random bits, they're information theoretically random bits, as long as the device was bounded during the execution of the protocol. Yeah, I'm done. And maybe just so I can't show you what the information theoretic analysis of this is, but we used results that were developed in the setting of Bell inequalities to argue that the min entropy specifically accumulates through n rounds of the protocol. That part is a little bit of technical, so I'm going to skip it and summarize and give you a couple open questions. So I described this protocol. It's a very simple 4-message protocol by which a classical verifier can interact with a quantum device. That has the property that if the device succeeds in the protocol and does not break the post-quantum cryptographic assumption, then this device must be quantum. It couldn't be classical. And more than that, it must generate randomness. And more than that, we saw how it generated that randomness. It was really by measuring a qubit in 2 mutually invalid spaces. So we got the start of a characterization of what this device was doing. So a couple open questions. I think that it's possible to do much more using the primitive and the ideas that were in this talk, and Urmila's or Mahadev's already done much more with it, so you heard her talk yesterday, and right after this she's going to talk about achieving quantum homomorphic encryption using similar ideas but expanding on them. One comment regarding my initial slide is that if you really wanted to implement this, and we did just really back of the envelope calculations, you need maybe a couple hundred qubits, maybe actually more like 400 qubits in order to implement this. And so there's a question whether you could fine-tune this and get a protocol that would actually be implementable on, let's say, 100 or 200 qubit device. And whether the device would need to be fully fault tolerant or not, I don't really know. So I think that's an interesting question to look at. Another question is whether you could remove the amount of or decrease the amount of interaction that's required in our protocol, maybe to have a single round protocol and move towards something that you'd call publicly verifiable randomness. So well, I'd have to define what this is. It's a little bit delicate, so let me not define it, and let me end here. Well, that's what I said. Yeah, for all I know, it's sufficient to have hundreds of perfect qubits.
Yeah,
and
but my point was 100 was about perfect. So it's not in the NISQ era, really.
Yeah, so that's why I said earlier when I had this little diagram, and I said I'm not going to answer the question, because for all I know, I need to multiply the 100 by 1,000, and then that's still too much. But I think that because of the simplicity of the proposal, it might be possible to think about how much fault tolerant is needed. So this device needs to do linear algebra. So the Trapdoor-Clough is really just a matrix vector multiplication in superposition. For all I know, that's still way too complex that you wouldn't need fault tolerance, but I think it might be interesting to look into.